So your team's down by 1 point, and Jimmy John here has the ball, and he takes the shot, and time runs out, but he gets fouled because the guy steps on his big toe. So he's going to go to the line and shoot 2 free throws, and let's say that Jimmy John is a 70% free throw shooter. And my question to you is it more likely that your team will win the game because Jimmy makes both free throws, or lose the game because Jimmy misses both free throws, or tie because he makes 1 out of 2? What's the most likely outcome out of those 3? Well, to answer that question, we could do an and probability. And that's the topic of Chapter 11, Section 3. An and probability deals with what's the probability that one event and then another event occurs. To do the last problem that I was just looking at, we would be looking for the probability as far as trying to determine if your team's going to win. We'd be looking for the probability that Jimmy makes the first free throw and makes the second. 2 events happening in succession. So the question is, how do we handle and probabilities? And we're going to get to that, but we can't get to it yet because to handle and probabilities, we have to use something called a conditional probability. And so we need to begin this section by figuring out what conditional probabilities are. So, Part A, conditional probability. And by the way, that is what it sounds like. It means we're looking for the probability of something under some condition that's been given to us. The notation for it goes like this. The probability of one thing, then a vertical bar, then another thing. What does that mean? Well, this vertical bar in mathematics is sometimes translated such that. I think a good way for us to think of it right now is to translate it with the words given that. So you could read this, the probability of A given that B has occurred. So that's the notion right there. We look for the probability of the first, assuming the second thing has occurred. So again, this would be the probability of event A, assuming that event B has taken place or has occurred. So what that does is it limits your sample space. It cuts your sample space down. Let me illustrate what I mean by it cuts your sample space down. Take a look at example 1 on page 596. It gives us a sample space of the following, the numbers 1 through 10. So I don't know, maybe we're picking a number from 1 to 10. Maybe that's the game that we're playing. You think, what's the sample space? Well, it's obviously all the numbers from 1 to 10. Now, if I just said to you, what's the probability of picking that the person would pick 3? Well, that'd be easy enough. That'd be 1 out of 10. But if I ask you, what's the probability of picking a 3 given odd, what does that mean? Well, what it means is we assume the second thing has occurred. We assume that the number that we picked was odd, and then we find the probability of a 3. So the second condition limits our sample space. In this case, it would limit our sample space to 1, 3, 5, 7, and 9, because we assume that the second thing has occurred. So if we limit our sample space to those 5 numbers, then there's only 5 things that can occur, and now the probability of getting a 3 out of those 5 would just be 1 out of 5. So a conditional probability limits the sample space. Okay, now, so what does that have to do with this? The probability of A and B. Well, here's a formula that will allow you to find the probability of events A and B occurring in succession. It equals the probability of A, and then instead of adding like we did with our OR problems, we multiply the probability of B given that A has occurred. So the second part of our formula is actually a conditional probability. That's how it ties together. Well, let's go back to some card problems to help us illustrate. Example 3 is on page 598. And that's not the problem I want. So the problem that I really want is example 9. Let's go there. Now I'm on page 600. If 5 cards are drawn, no, I don't want that one either. David, come on. Okay, I'm going to make up my own problem because the problems I had on my lesson plan didn't say what I thought they said. So here you go. Let's just call this an example. 2 cards are drawn from a 52 card deck. Find the probability of drawing a face card and a 5 in 2 successive draws. That's the kind of problem I was looking for. So what I keep saying on as we move through these chapters is we have to recognize what kind of problem that we have, okay? And obviously this is probability. It's not how many. It's not a counting problem. And it's an and. So once we recognize that, we automatically jump to this formula. Okay, well let's jump to that formula. So the probability of getting a face card and a 5 is equal to the probability of getting a face card times the probability of getting a 5, given that I got a face card. So this is the stuff over here that we got to figure out. Okay, now one thing I did not mention on this problem is if you get a problem like this dealing with cards, the problem should either tell you we're replacing the card or we're not replacing the card between draws. So on this problem, I want you to assume no replacement, meaning we picked the first card, held it in our hand, and then picked the second card. Some problems will tell you to replace the card, which means you pick the card, put it back in the deck, and then pick the second card. Okay, so we're going to assume no replacement on this problem. So, what's the probability of getting a face card on the first draw? Well, we counted these earlier. We got the Jack, the Queen, and the King. That's 3 cards in each suit. There's 4 suits. That makes 12 cards out of 52. Times, and now we're going to assume that we got a face card on the first and find the probability of picking a 5. Okay, well, if I got a face card on the first, then the probability of getting a 5 on the second, there'd still be 4 5s left in the deck, but I'd only have 51 cards left in the deck. So to figure this probability, I would take 12 out of 52 times 4 out of 51, and I'm punching that in on my calculator. That is a decimal of approximately 0.018. If you want it exactly as a fraction, that turns out to be 4 out of 221. So not very good probability of picking a face card and then a 5. Okay, so I want to ask you guys a question. What if I would have said replace the card back into the deck? Then how would that have changed my problem? So I'm going to ask Chris and Tristan, would the 12 out of 52 have changed? No. No, because I'm still just picking a card. Would the 4 out of 51 have changed?
Yeah.
How?
4 out of 52.
That's right, because we put the card back in the deck, we still would have had 52 cards in the deck. It would have been 4 out of 52. That's right. Okay, now let's look at a few other problems here. So we can apply this rule a few more times, get a little more practice. I'm looking at example 8 now. It's kind of funny because it talks about an urn, which, I don't know, most people when they think of urns, they think of if someone's been cremated, a lot of times they'll put the ashes in an urn, but this urn is not holding ashes, it's holding balls. It says Annie is drawing balls from an urn, shown at the side. This time she draws 3 balls without replacement. Find the probability that she gets red, yellow, and blue balls in that order. So this time we're looking for the probability of what was first there. Red, and then yellow, and then blue. So we still have another and problem. The only difference is this one has 3 events instead of 2 involved. But we can extend the notion behind this formula that we started with. So that equals the probability of red times the probability, it should not be an R, it's supposed to be a P, the probability of yellow, given that, or assuming that I got red on the first, times the probability of blue, and when I look for the blue, I'm going to given that, or assume that, we got red and yellow on the first 2. Okay, here goes. So if you look at the urn on page 600, there are, what have I got there? 3, and then 4 is 7, and then 4 is 11 balls in that urn, and 4 of them are red. So 4 out of 11 probability of getting red. Now let's assume that we got red and that we didn't replace it. So now what's the probability of picking a yellow? Well, I'm counting 5 yellow balls in the urn. And if I did not replace the red ball, then I only have 10 balls left. 5 out of 10. Times, now we're going to look for the probability of getting blue. There are 2 of those, assuming that we got red and yellow on the first 2. If we didn't replace them, then there's only going to be 9 balls left in the urn. So, you know, sometimes your calculator's quicker, sometimes you're quicker. I mean, think about this. 2 would cancel with 10 and make 5. 5 and 5 would cancel with each other. So really we'd have 4 in the numerator and 99 in the denominator. So the probability of getting red, then a yellow, and then a blue without replacement is 4 out of 99. Well, let's continue to think in the fashion we've been thinking. Example 9 will allow us to do that. It says if 5 cards are drawn without replacement from a standard 52 card deck, find the probability they are all hearts. And you say, well, how is that an and problem? Well, it's an and problem because if they're all hearts, that'd be like getting a heart on the first and a heart on the second and that would continue until I got a heart on the 5th. So all means the same thing as and for how many events that you have. Okay, now if I apply this notion that we've been looking at with the last couple of problems, this problem would go like this. I would first look for the probability of the first. So if I pull a card out of a 52 card deck, I have 13 out of 52 probability of getting a heart. Now I have to remember if I'm replacing or not, and on this problem it says without replacement. So I'm not replacing. So I'm going to assume that that happened now, and I'm going to find the probability of the second. Well, if I assumed it happened, then the first card that I picked was a heart. It's sitting out now. So I've only got 12 hearts left out of 51 cards left. Now I assume I got heart on the first and heart on the second. I go and find heart on the third. Well, now I've only got 11 hearts left out of 50, and now you can kind of get a feel for how this is going to go. The fourth heart I'd have 10 hearts left out of 49. And the fifth heart, I'd have 9 hearts left out of 48. And if you crunch the numbers there, you end up with 0.000495 according to your textbook. Now, that's probably how I would have done that problem. But if you tie this back with what we've been working on in this chapter and what we worked on last chapter, let me show you another way we could have thought through that problem. Let's go back to our definition of probability. The probability of all 5 hearts would equal the number of ways I could get all 5 hearts over the number of items in the sample space. If we start with the sample space, we've actually done this problem several times now. How many 5-card hands are there? Well, repetition's not allowed, and in your hand, the cards, the order you get them doesn't matter. So I could use a combination. I could choose from 52 cards, I could choose them 5 at a time. Now, thinking in terms of how many of those are all 5 hearts, again, repetition would not be allowed, order wouldn't matter, but I'm not picking from 52 cards anymore, I'm only picking from 13. So that'd be a combination of 13 things, 5 at a time for the numerator. If you do a 13 combination 5 divided by a 15 combination 5, you're going to get this number again. Exactly. So that's another approach you could have taken to get it. So I don't know, that's one thing I think is so neat about mathematics, is if you take a solid approach, you know, there may be 2 ways that look entirely different to think about a problem, but they're going to end up at the same place in the end. Well, there's a word that's thrown around in your homework that you might run across, so I want to make sure you're familiar with it in case you do. And the word is independent. What does it mean for 2 events to be independent? Now, what I usually do when I teach this is I put the camera on one of my students and we play pretend for a moment with a deck of cards, but I don't have a student here. Okay, so here's what I want you to pretend. Here's Mr. Card Dealer. Here's the table. And over here is sitting, we'll call this Tristan this time. Black hair, near shoulder length, and sitting on her chair there. Okay. What the dealer is going to do is he's going to fan out a deck of cards in front of Tristan. Here are all the cards. But it's a whole deck, so there's 52 of them. And what we're interested in is Tristan picking a jack on the first card and let's say a king on the second card. Okay, so here's all 52 cards. It looks like there's only 5 there, but really there's 52. Okay, Tristan reaches out and picks a card. Tristan, can you look at your card really quick?
Yeah.
What'd you pick?
9 of diamonds.
She picked the 9 of diamonds. Okay, let's say this time we replace the card back into the deck. So she looks at the card, then puts it back. Now, Chris and Katie. By the way, that's supposed to be a D there. It looks like a P. Chris and Katie, what's the probability that she's going to get a king on the second card? Let me talk you through it again. Here's what happened. They fanned out 52 cards. She picked one up. She looked at it. It was the 9 of diamonds. She put it back in the deck. He reshuffled the deck, fanned the cards back out in front of her, and I'm asking you guys, what's the probability that she picks a king on the second? 4 out of 52. Now,
4 out of 52.
okay, you said 12, but you meant 4. Okay. Here's the deal. Here's the question I got to ask you. Did it matter whether she picked a jack on the first one as far as what the probability of her getting the second one in that scenario? I mean, whether she got a jack or not had no bearing on the probability of her getting a king. The probability of her getting a king there was going to be 4 out of 52, whether she picked a jack on the first card or whether she didn't. You see what I'm getting at? Head shakes? Okay. So in that case, these two events are said to be independent. Independent means whether the first one happens or not, it doesn't have any bearing on the probability of the second. Let me say that again. Independent means whether the first event happens or not has no bearing on the probability of the second event. Okay, now I'm going to change this problem a little bit because it'll be easier to illustrate if I change it. So this time, instead of saying she gets a jack and a king, let's say she gets a king and then a king. And this time I want her to replace the card. I'm sorry, I do not want her to replace the card. No replace. Okay, so the dealer fans the cards out in front of Tristan here. She picks a card. So Tristan, pick your card up. I want you to look at it, but I don't want you to tell us what it is this time. Okay, set it down there beside you. She sets the card beside her. Now, here's my question. What's the probability she gets a king on the second one? What do you think it is, Katie? The probability of her getting a king on the second card? Same. Same as what? But she kept the card this time. She didn't put it back. You see this arrow going back? It's gone now. She picked the card and she kept it. So now what do you think the probability is? Okay, she thinks it's 3 out of 51. Chris, what do you think the probability is?
Well, we don't know what that one card is, so.
Oh, that changes things, doesn't it? If this card is a king, then Katie's right. She's got 3 out of 51 probability of getting another king. But if this card is not a king, then she has 4 out of 51 probability of getting a king on the second card. So the second event, the probability is dependent upon whether the first event occurred or not. So if we don't replace the cards, then these events are not independent. If we replace the card, the events are independent. But I'm getting at the bigger picture here of what independent means. Independent, again, one last time here, means the probability of the second thing is not affected by whether the first event occurs or not. So that's what independence means. If I roll a die and then flip a coin, what I get on the coin is not dependent in any way by what I get on the die. So those events would be independent, but some events are not. Okay, so if you see that, that's what it's talking about. Now, let's get you an assignment for this second page here, and I can get some light here to help me. How about, and I've got that marked out, so it must not be good. Okay, page 603. So don't run off after we get this assignment written down here. I got a little bit more for us to think through. 2 through 4, 13 through 20, 23 to 27, 45 to 47, and 63 to 65.